Good day, we are from Group 29. For this assignment, we will be presenting on the third law of thermodynamics. Let us give you a brief introduction to how the third law of thermodynamics was first postulated. This law was coined by the renowned German chemist, Walther Hermann Nernst in 1906. Nernst started experimenting with chemicals in the light to increase nitrogen-based fertilizers using varying pressures and temperatures of different chemical reactions. He then applied the principles of thermodynamics and postulated that if the temperature of the object approaches 0 Kelvin, the heat capacity also decreases to 0, which means less heat is required to raise its temperature. Even though Nernst had made an excellent discovery, he lacked theoretical evidence. And here comes Einstein and Planck's contribution to prove the theorem to be, in fact, true. This law is also otherwise known as the Nernst heat theorem. It is defined as, for any substance in internal equilibrium, the change in entropy of the substance goes to 0 as the temperature drops to absolute 0, provided the process is in an isothermal condition. The third law allows us to calculate the absolute value of entropy, although it is impossible to achieve in classical thermodynamics. Next up, let us discuss on the theory behind this law. As the temperature of a system which is in internal equilibrium approaches absolute 0, the heat capacity also decreases, therefore, the entropy change is equal to 0. The attractive force between atoms increases as heat is released to the surrounding, forming an orderly arrangement of a perfect crystalline structure as the temperature and entropy become 0. Based on animation 2, at absolute 0, atoms would still be able to vibrate but would not change their wave pattern and not have enough energy to change state. This is an example to calculate standard molar entropy, delta S. Before starting to answer this question, we need to separate the molar entropy into 4 parts. For the first part, the by-extrapolation method was used to calculate temperatures that are close to absolute temperature. Next, we plot a graph of CPM against ln T. From this we can notice that the graph is practically a linear relation. We can then extrapolate to the melting point. Then, we calculate the area under the graph by assuming the graph is a trapezium shape. Hence, we can use formula 2 to calculate the area. For the fourth part, we calculate the molar enthalpy of fusion and divide it by the melting point in Kelvin. Lastly, we need to substitute the values of A and B into the CPM that is given for the range integration of CPM over T dt from 161 Kelvin to 298.15 Kelvin. After that, we can get the last entropy value. Finally, we just need to add on all the values from the parts and the entropy of carbon disulfide in 298.15 Kelvin gain.